Good afternoon to all of you. Welcome to the oral session on performance evaluation of the International Monitoring System and on-site inspection and their components. I hope you had a chance to join the poster session this morning. I introduce myself briefly. I'm Thierry Thier. I am from the PTS, the Office of the Executive Secretary dealing with evaluation. And I am co-chairing the session with Madame
Anne Lykke, who is the manager of the NORSAR group.
And my name is Josep Villa. I'm Senior Evaluator of the Quality Management and Performance Monitoring Section, the Office of the Executive Secretary under Thierry as Chief.
Thank you. Then we are ready for the first presentation, and that will be given by Samuel Kristoffersen on the theme of the use of in situ calibration for real-time infrasound station monitoring and improved wave parameter determination.
Okay, thank you. This is the next slide, previous slide, and that's not a laser pointer. You want to choose this next, so just previous. Yeah. Just this. Okay, great. Okay, thanks. Yeah, thank you for the introduction. And once the slides show up, I'll be talking about on-site, real-time on-site calibration. And there should be other authors on there, so I apologize to my colleagues at CA and BGR. That's an oversight on my part, but this work wouldn't have been possible without all of my co-authors as well. So, to start with the measurements of infrasound at any IMS station or any infrasound station, to get measurements of, for example, back azimuth and trace velocity, we need to use basically the time difference of arrival at each. So there's an array. So if we imagine, here we go. Imagine we have an array like this of several detectors at a station, and the difference of arrival time allows us to determine azimuth, trace velocity, and basically direction. And for my study, I was using PMCC, but there are several different methods for doing this. And one thing that's interesting is sometimes there are situations when these sensors don't operate 100% capacity. That there might be issues, like for example, if there's flooding in a wind noise reduction system, then this could cause errors in the arrival times, and we want to see how does that affect the results, and two, how can we correct those results. So, as I mentioned, the wind noise reduction system, well, these are at IMS stations anyway, they use these pipe filtering systems to reduce the wind noise created by wind. And the idea is that basically with a passive on-site calibration, we can determine what the response of these filtering systems is very precisely, because obviously anytime you connect pipes to a microbarometer, you're going to affect the infrasound response. And if there's defects, we'll be able to observe these defects, and in addition, we can use that calibration to correct for potential errors. And one thing to note here, so this is the calibration is done with a co-located reference sensor, which is typically going to be, which would typically have been either in the lab or on site, calibrated with a reference that would match back traceable to SI units. And so that's where we have our reference calibration. So the Gabrielson method, which I think is has been talked about a few times at this conference before. Basically the idea is having this co-located reference sensor with the system under test. So for example, in here we've got a reference sensor located right at the center of the wind noise reduction system. And that allows us to use ambient acoustic signals to measure the relative response of the reference to the system under test. And basically by taking that relative response, we can determine what the response of that sensor under test is. So it's basically just a comparison calibration. and we use only periods, windows where there's very high coherence to ignore situations when there's noise, and that allows us to get this calibration by reference. So the experiment that I'd set up to see what the effects of this defective system was by putting a temporary wind noise reduction system, a temporary sensor, at IS-26, co-located with element H5, which is sort of on the outside of the array. And the idea was that we could have the IS-26 measurements, so we weren't touching those, and it wouldn't have any effect on those, but we would have those as sort of our reference to sort of have not a ground truth, but I'll call it a ground truth, because, and that way we have something to compare it against, and we can play with our temporary system, blocking pipes, and adding defects to see what effects they have and what would happen. So here's just a couple pictures of the setup. So we can see on the picture on the left, there's the system under test with the 4 pipes coming out of it. So that's connected to the wind noise reduction system, and then the reference sensor with a small tube that allows that inlet to be as close as possible to the center of the wind noise reduction system. And the picture on the right is just another picture of the wind noise reduction system tubes, alongside the white discs are the wind noise reduction system of the H5 element, the IS-26 element. So for the temporary system, we set up 5 experiments. One was just a nominal, sort of as a sanity check to make sure that the system worked, and we got good results. Then we had 3 defective systems where we blocked 8, 24 inlets, and then one where we disconnected a pipe from the microbarometer, and then one where we buried the reference sensor inlet just to see what different effects. For this talk, because there's not a lot of time, I'm just going to focus on the 2 blocked inlet cases, the 8 and the 24 blocked inlet cases. So for the 24 blocked inlet cases, we can see on the right here's a plot of the gain. So basically the calibration response of that system under test with 24 blocked inlets. So normally we would expect the response to be relatively flat up until at least 4 hertz. But we can see because we block these inlets, now we're getting a resonance between 1 and 2 hertz. And in addition, there's a fairly large phase dip that occurs just after this resonance, up to, of about almost 150 degrees. And of course, 150 degrees phase error will have an effect on the timing of the time delay of arrival, essentially. And so that obviously could be a problem for PMCC measurements. And so what we did here is just some of the results. So this is I'm focusing just on 2 to 3 hertz right here. And we can see the blue circles, pardon me, are the IS-26 results. So again, what I'm considering to be sort of my reference. So these are the correct results. And the system's working normally, so it's a good system, so they should be good. The orange dots are the results using this temporary system, this defective system, instead of H5. So this is replacing 1 out of the 8 elements with the defective system. And we can see in the azimuth, in the speed, and in the amplitude, all 3 of those estimations, there are clear biases that show up in the results. So a few degrees in the azimuth, almost 20 meters per second in our speed. And it's difficult to say exactly in the amplitude, but there's clearly a bias in the amplitude. And this is just above the resonance, so we're actually seeing the amplitude look smaller than we would expect. And the really exciting result for me was that when we used the calibration to correct the signal, so these are the yellow dots, basically we deconvolved the signal using the calibration, and that result gave us almost exactly the same results that we got with the H5 element. So we're able to correct these errors, these biases that were showing up due to the defective system. And so quickly, I'll just show another example with the 8 blocked inlets. The biases are slightly smaller here, but it's the same idea. Again, you can see that there's a degree or 2 error in the azimuth, 5 to 10 meters per second, or maybe not. a few meters per second, 5 meters per second, a few meters per second in the speed, and again, we can see biases in the amplitude, and we're able to correct those. Again, the yellow dots are matching almost perfectly with the H5 results. And so one final example I want to give is, so those were with this temporary system that we had set up, but this is an example of the Hungatunga eruption at IS-47. So there was an issue with one of the, I think there was a vent or something that wasn't properly, when it was installed, it wasn't installed quite properly. And at the time of the Hungatunga eruption, this issue hadn't been resolved. It has since been resolved. But as the result, when we look on the images on the left, we can see that the azimuth at the top, speed in the middle, there are clear gaps as it doesn't go all the way down to our 10 millihertz. And also, particularly in the speed, we can see that the speeds start increasing significantly, which you wouldn't expect 400 or 500 meters per second in this situation. But if we look at the figures on the right, we can see that once we've applied this deconvolution, corrected using the calibration, that we get all the way down to our 0.01 hertz, and the results match quite well with what would be expected for this eruption. So just to sum up, this method has worked well. It's able to show defects in our systems quite well as we're able to use this to monitor station health, which is sort of currently being done, or I shouldn't say sort of, is currently being done, but in addition, in instances where there are issues, these calibrations can be used to correct potentially those results and provide us with the correct PMCC or other time delay of arrival type results, azimuth, speed, and so forth. So thank you for your time and attention.
We have time for a question from the audience, if there are any comments or questions to the speaker. If that is not the case, then we thank you so much for an interesting presentation. Thank you. And then we have the pleasure of inviting Mahmoud Salam for the next talk about the fuzzy rule-based expert system for seismic stations data and quality analysis. The floor is yours.
Thank you so much. My presentation is about using one of the techniques of artificial intelligence. It's called fuzzy logic to be used to calculate or determine the quality of seismic noise. My agenda today is motivation and a simple introduction about the BSD, and also a simple introduction about fuzzy and fuzzy systems. Then proposed framework could be used to calculate quality for seismic noise, and some result and conclusion. My motivation for doing this tool is to calculate the quality parameters for the seismic station. Quality parameter for seismic station can be determined by time accuracy and completeness and many other parameters. Especially ambient noise levels could be calculated or determined by simply using some threshold, like completeness or gaps or time accuracy. But quality for seismic ambient noise could be done through the checking or inspection, virtual inspection of the waveform itself, or even by calculating the power spectrum density and periodically, and check it also by the operator or an expert. This process could have time-consuming, very time-consuming, and you also need to have some expert. So my motivation is to do an automatic quality control system that able to calculate or determine the quality of seismic station automatically without need to or replacing the expert. About the power spectrum density, it's a tool could be used to convert seismic wave from time domain into power spectrum domain, and use this domain to judge the quality and determine if there is any problem or any issues, just like dropping packets, or there is a high noise due to civil living human around the station, or even some defected instrument or calibration done in the station. So using power spectrum density as the base of our system will make it easy for human to judge, and also for artificial intelligence to judge and calculate some quality parameters. As an introduction for fuzzy logic, it's different logic. It's different from Boolean logic, which is binary logic or two values logic, while the fuzzy logic is multi-value logic. It doesn't consider only 0 and 1 as a membership or as a value for absent or existing of the element, but it somehow can calculate some membership of absence or presence. The second difference between the fuzzy logic and normal logic, that in normal logic, the element must be exist in only one subset or in any set. But in fuzzy logic, the element can be exist with different degree of membership in different subsets. Which it's like the human thinking. The human thinking is like fuzzy. If I'm considering tool to judge the tool of any human, I can't just say that less than some height is considered short, or above this is considered high, or above it considered tall. But it somehow the human or the tool can be somehow average and somehow tool membership with some degree in this set or in this other set in the same time. Also, if we have a different logic, we must have different rules than the simple rules that can be used in Boolean logic, but it's almost in the same figure. It's if-then rules, and also use some operators like and or to merge and combine conditions. But here, in our condition in fuzzy, it uses linguistic variables. It checks if the element or the value is exist or a member of a specific set, but with some degree of membership. And also firing this rule could be partially. If the inputs are partially exist in this subset, also the output is partially exist in the output subset. My proposed framework is very simple. It's simple data flow. It used all of it are written in Python based on OpenSpy package to do the data extraction and data processing, and skfuzzy to do the fuzzy system. The system is started with extracting the waveform itself for a specific station, specific channels, then calculate the power spectrum density, then phase to extract the important feature that the expert need to use it to express his knowledge or his expert to convert it into simple rules. Then by this extracted feature, the fuzzy system can use it and use the fuzzy rules that have illustrated and imported by the expert, and can calculate the quality. It can calculate different parameters for quality, and then it can store back to a database for the quality of the station. This process can be done daily, monthly, and even yearly. And this system is built by multi-threading system, so it supports parallel processing, so it can handle more than one channel or one station in the same time, depending on the workstation capabilities. For the first new stages, after data extraction and converting and calculating power spectrum density, feature extraction is done by calculating the relation or the relation between the power spectrum density and its relation with the new low noise model and new high noise model, which now are the standard for noise level comparison. So we consider the station in a specific frequency range is good if it is near for low noise model and far from high noise model. By calculating the percentage goodness for all of these stations or of all this frequency, specific frequency bands or frequency values are selected to be input for the fuzzy system. The fuzzy logic system is consisted by four parts. The input part that can use as a fuzzifier or fuzzification stage, which convert the real values for the goodness into a fuzzy domain. Then the rule base, which consists of different rules that has been expressed by the expert to judge the quality of the station based on the input, and then the inference engine, which use these rules and fire it as it need based on the input values itself. Then the final stage is the defuzzifier or defuzzification, which are the part of returning back the values from the fuzzy domain into real world domain. All of these parts each part have a different configuration file, a simple XML file. We can see its format like other file. For the first stage, the fuzzification, as I mentioned, it takes inputs like this one. We have 4 inputs. We have 4 frequency range, low and medium and high and the ultra high frequency range. Then I can make it in different sets, low and medium and high, so I can convert the goodness value for each part or for each frequency band into a membership values for each subset, each set. Then after, this is the XML file that describe the fuzzification stage. It's an external file, so as I need to add more inputs, I can just modify in this file, and also I can modify the values to start and end of each set value based on the expert opinion. Second part for the fuzzy system is the rule base. The rule base consists of many rules, very simple rules that can be expressed by normal English sentence. If then rules, it has a relation between the output and all the input, some of them or all of them. The most important thing in this rule base, it can be modified and add more rules as the expert or a new information came, so can modify rule base to and add more quality parameters as an output. The final block in our model for fuzzy is the inference engine, which have a great rule for merging the rule itself and fire it based on the values, and then the defuzzification part, which is responsible about converting back from the fuzzy domain into the real world domain and calculate single value as a quality parameter for each output parameter, which will be the final decision for the quality. This is also the conversion file for the quality output. This is some result based on real data. starting from waveform domain, then converting it to power spectrum density, then calculate all the feature on goodness and compare it with the standard noise levels. Then extract the input for the system. Then it will have calculate a single value, which is be here almost 70% for this channel. Also another result for not a very good station. It have a lowest value for as a quality. The most important thing about this framework, it can be used regularly in routine work without intervention of any human. It can get the data directly from the data store and convert it into a quality value, which can be used as to monitor all the station in a single dashboard. And this dashboard is can be changed every day and can have different dashboard, monthly, daily, yearly, and even seasonally. My conclusion is the importance about using an automatic system can be judge the quality for seismic station, especially could be used for ambient noise quality parameters. The most important thing about this framework is it's dynamically, so user can add more input parameters and calculate different output parameters, and also modify or enhance rule-based to add more knowledge and more experience to the system, replacing the need to have a human expert to check and inspect all of this data, which can consume a lot of efforts. Thank you.
Thank you so much for the insights into fuzzy logic. This is quite new for me, but I hope there are many questions or comments from the audience. If there are not, then I'm sure that you will be contacted in the break. Thank you so much.
Thank you so much.
Then it's a pleasure to welcome Bayaraa Jargalsaikhan. I'm sorry about the pronunciation to begin with. You are going to talk about the detection capability improvements of the MNDC in the last 10 years.
Good afternoon, everyone. My name is Bayaraa. I'm working for Institute of Astronomy and Geophysics of Mongolia. So today's my presentation is a detection capability improvement of a Mongolian NDC in the last 10 years. Okay, so there is an outline of my presentation. There is a brief history of the seismic station of Mongolia, and regional stations and its improvement, calculation method of the detectability, and power spectrum density of Mongolian seismic station, and detection capability calculation and the results, and at the end, and conclusions. Okay, so to do present capability, I need to historical briefly. So the Mongolian first station is built in 1957, and paper-based Russian stations installed at that time. And then also this 1957 is a very big earthquake occurred in the Alta mountain. Okay, so after that, 1958 to 1988, there is 7 more analog stations, paper-based analog stations installed, helped by Russians. Then first digital station is installed in 1994. It is around Ulaanbaatar area, between 25 to 75 kilometers far from Ulaanbaatar, helped by French colleagues. And also that there is there's USGS installed ULN station close to Ulaanbaatar. 2002, IMS PS25 array station installed with 9 elements of vertical component, short period CM400, and also long period installed. 2008, we have built own Mongolian NDC. Then we can monitoring, analyzing own self to all of kind of data. 2013, there is a Ulaanbaatar monitoring geophysical station installed around Ulaanbaatar city. There is 16 stations installed. Also, ULN has upgraded own stations. 2014, 3 new regional stations has been installed in the Seling, Bogd, and Mandalay, which is after extended 1988, extended 3 more stations. There is also local operators working on that data. 2015, early warning system for installed around UB array, where is a very active fault installed. Each one is 4 stations, and there are 3 different active fault. We installed this one. And 2017, 4 automatic station has been installed east side of Mongolia, and 2018, 5 short period automatic station has been installed west side of Mongolia. And at last 2020, the broadband station installed north side of the Mongolia, because 2021 there is a big earthquake in the north, Khupskul Lake, 6.4 around big earthquake occurred. There is, I want to show you, 2005, there is all of the paper-based pota paper station changed by a short period station. Blue one, it shows the places where we installed it, and which one is finished 2005. And 2011, we changed all of them by broadband station. Green one is a broadband station location. And 2013, there is all of them is broadband station. Also, some station extended. 2014, we extended 3 more stations. Locations you can see. And the red one is accelerometry station inside of the city, small city. 2015, we have red dot shows the early warning system, where is active fault around UB. 2016, east side, we installed a broadband station. And 2017, another broadband stations we have installed. And then 18, short period station installed west side of Mongolia, because west side Mongolia is more active, seismic activity is more than east. 19, we have installed a lot accelerometry stations. And 2021, there is a north side of the next of lake, we have another station, Sam station is installed. Okay, so there is a 3 kind of changing migration between station improvement. First of them is pota paper station installed. Then which one is finished, migrated to digital, short period station between 2005 and 2007. And 12 regional stations is replaced digital stations, which one is a short period, sale stations. And that time we are transferring data through the flash disk via post. 2010 to 2011, all the regional short period stations were swapped with the broadband 3 SPC and a Goralf digitizer, new station installed. Also, all 12 regional stations connected by fiber optic cable. Okay, so next one, detection calculation method of the detection capability. Calculation of noise amplitude of displacement at each station from the corresponding PDF of power spectral density in frequency domain. Use it software PQLX, and Nakamura and the BOS written it. And PPST in OPSY tool we are using. And second one is a ground displacement amplitude attenuation expression of the Dr. Ulzibat uses to calculate minimum earthquake detection threshold of the stations related by distance. Okay, there is a spectrum of the broadband station I want to show you. First one is Almar O4.1 is broadband stations, and the other one is just surface stations. All of them is broadband stations. Which one is between the 1st of January 2019 to 12th of May 2021. 3 years data we are using to make this calculation. Okay, so there is another stations we have. There is 3 years, little more than 3 years that we are using. Also, we have a lot of quiet stations in Mongolia, but also we have another not good stations we are still using, which one is 60 dB growth stations, which one is maybe some side effect is more than others. Okay, so there is, for example, one of them station is, we have 5 years data, 5 years calculation you can see. There is a PST between 2014 to 2019. So there is all of the PDF, it's 95%, 95, 90, and mean, medium, and mode. You can see one of the center of Mongolia, there is like this spectrum, one of the stations you can see like this. Okay, so to do this, we need to PST disable to apparent displacement of this calculation. So this is Hapsko and Kusil 2006. It is they made this expression. So which one is disabled to displacement? The maximum amplitude in the corresponding time window are 3 times more than average peak amplitude. That's why it's multiplied by 3. Okay, my center frequency is 2 because this center frequency is very, mostly it is 2 to 10 hertz should be, but my shows it center frequency is 2 hertz. So which one is shows under one of the example is the BNB station with the west side of the station. So there is a rounded number of the period, 0.5. It's 2 hertz, and the power is minus 144. So the calculation you can see to nanometer, the bottom of the numbers, 0.25 nanometer of the calculation using this theory. So there is, we are using a 90 percentile of 90 because it is a worst case, maybe wind, and other case, that's why we're using 90 percentile percentage of in the 2 hertz. Okay, then we know the every station's own noise in the nanometer. So there is this all of broadband, all of these stations on the Z component you can see. Okay, after that calculation, attenuation from the epicenter to station using Dr. Ulzibat ML scale equation, which ones we are using this one, and the delta is distance between seismic station and epicenter, A and maximum ground displacement amplitude. Okay, so to do this, we create a grid and the calculate to epicenter station R between the grid point and each station for network capability estimation at the regional scale. Epicenter distance can be used as an approximation of the epicenter distance. For a range of values, calculate each station maximum ground displacement amplitude A from the equation from ML scale. To find the smallest ML value, which condition at least 3 times more, because this is more than noise level. That's why 3 times. And this one should be also meet at least 4 stations should be detected like this. Okay, this is between 2011 to 2016. There is detectability in Mongolia. You can see around magnitude 2 is all the stations can detect. Mostly west side of Mongolia and the center of Ulaanbaatar, there is a lot of stations. That's why it's more magnitude, minimum magnitude is detectable. And 2016 and 2021, there is also extended stations, also improving detectability in Mongolia. So, and right now there is all the stations looks like this, and almost 1.4 magnitude, 1.4 is whole Mongolian can detect our whole Mongolian territory. Okay, so conclusions. In the last 10 years, MNDC extended totally 39 stations. In Ulaanbaatar, 16 broadband stations were installed near Ulaanbaatar city. In regional, 8 old short period stations were updated with the broadband station, and 12 accelerometer stations installed for purpose of early warning, and 5 short period stations were installed west side of Mongolia, and 6 broadband stations installed east and north side of Mongolia. So the result is detection capability of the seismic network Mongolian is increased from the magnitude ML to 2 to ML 1.6 in whole territory of the Mongolia. So source of site citation, there is a Asian cost seismic network capability assessment software tool regional network example is Martin Mulhoff, and also instrument seismology of SCO, and other software programs we are using. Thank you.
Thank you for this valuable insight into the Mongolian improvements. That was really interesting, and I hope that there are some comments or questions from the audience to this. Yes?
Thank you. Thank you for a very nice presentation. I have one comment and a question. I think for the BSD, you showed us, especially for the short periods, they show good level of noise, but they are higher just in the low frequencies, the higher period, the longer period, which is they cannot catch. So it's better to scope for short period, just the shorter period waveform. My question is about the detectability. You mentioned about the detectability for the network in the last 10 years. Did you compare this with your completeness, the catalog completeness, to check about?
Yes, I have a completeness made, but it's I still need to work on this completeness. I have compared catalog and with my pictures, but I need to a little bit working on this because this is a magnitude almost minus below than -1, a lot of earthquake we can detect. So which one is, I need to relationship between them exactly. Which one is next presentation I will make.
Yeah, the next question is from Tormod, Kvaerna.
Yes, thank you for a very nice presentation. You have the IMS array located in Mongolia. I just wondered, do you take the effect of the array processing into account when estimating your capabilities, or do you plan to do so? Thank you.
Okay. We have an IMS station, but right now we not. Which one is close to Ulaanbaatar city? That's why a little bit noisy. Then so I will.
Thank you so much. I think we need to go further in the program and move from detectability in Mongolia to detectability for the whole system. So thank you again.
Thank you.
Oh, yeah. Yeah, we'll do that after. Then we introduce Tormod Kvaerna, who's going to talk us through the IMS system detection capability with a method called threshold monitoring. And there is an online question to the previous talker, so we will take that up afterwards.
So thank you for this introduction. I'm going to present a new tool that we have developed at NORSAR as a contribution to the IDC re-engineering program. It's a web-based version of threshold monitoring for estimation of network capability of the IMS system. Just some background information about network capabilities. Of course, it's important to evaluate how existing or planned or hypothetical networks will perform. And you have to consider different scenarios, like when stations are out of operations, how the noise levels vary, how the event definition criteria apply. Sometimes you request 3 stations, sometimes 4 stations, and also different probabilities of detections. And common for most of this method is that there is a model for how the seismic waves propagate through the Earth. And a well-known model is the so-called Waite-Clausen distance-dependent P-wave MB corrections that you see on the lower part of this slide. That is commonly used for P-waves. There was earlier today a very nice presentation on a poster by Sandia Group and also by the IDC on how they use the NetMod tool for evaluating the performance of the IMS system. It's based on statistical models for noise and signal, but also more realistic noise models, so observations made at the IDC. We also have developed, together with my colleague Frode Ringdal, a method for evaluating the capabilities based on the reviewed event bulletin. That is also giving some sort of global overview of how the detection performance works. But both of these methods, they present what we call average probabilities. Just an example, you can see how it was in 2015 as compared to 2023 when you have additional stations reporting data to the IDC. So you see that there are improvements in Northern Europe and Asia when new stations are coming in China and Russia. But of course, the average properties does not always apply. And what they show here is, this is the day of year of 2011. This is about time period from January to October at noise level observed at the station Yellowknife in Canada. And you see here that during summertime, you have very much higher noise levels, about 1 magnitude unit higher amplitudes as compared with the winter condition when the nearby lake is frozen. You also see large signals coming in, and you see here this Tohoku earthquake that occurred in 2011 give a very large increase in the amplitudes for a larger time period with the main event and the aftershocks. And in addition, you have station array sensor outages, communication gaps, data processing failures that came into play when the performance of your system will work. At NORSAR, we have developed what we call the threshold monitoring methodology, which is currently processing data at the IDC, providing capability data at every 10 seconds of the system. And these results are available at the IDC. They are also available to the secure web portal in terms of 1 hour averages and worst case situations that you see on the plot here. And to the right, you see that the effect of an event in Kuril Island very much deteriorate the performance on the average for this time period. But the data for the threshold monitoring has a much higher resolution and much more to give, and therefore we at NORSAR embarked on a project to develop a software tool for which both the IDC and state signatories can assess the performance of the IMS primary seismic network. So we have developed a web application, we'll show you in a moment, where you can select the time interval of your likes, what you like. You can define color scales, select geographical area of interest, and we envisage that this tool will be made available to MNDCs, to PTS, and to authorized users of the web portal. So currently, we have developed a prototype. There is a tutorial available, and we have to develop some additional functionality at the IDC to make this data accessible by the users. And testing is currently ongoing at the IDC. So in order to demonstrate this tool, I didn't manage to have a real-time demo of this, but what I did was to sort of run a session locally on my computer at NorSAR, accessing data over the internet from the IDC. And then I have recorded this session in a few video clips, and I will try to comment as the video is going on. I haven't practiced that much, but excuse me if it doesn't work too well. But let's go for the first video clip here. So first you have up a standard web browser, maybe the web portal. You access the address of the tool. You have down to the left that time window of analysis. This is the 1st of June this year. You get instantaneous threshold at the end of the time interval. You may see a small cursor moving over there. You can see this is the time window area that you select. You can compute the average during this day, and suddenly the contours update, and this is a real-time display of how it works. You have different stations shown depending on the colors. Green means data available is 100%. You have stations that are black that doesn't have data contributing at this time interval. And you see also that the detection levels in the northern hemisphere is far better than in the oceans. To the right, there is a series of buttons for which you can click and have different functionality. For instance, you can turn off the color map, turn it on again. You can, of course, turn off the contours. You can turn off the stations. You can also show the station labels. You can also display the different target points for which the thresholds were calculated. And by hovering with the mouse and the wheel, you can zoom in on an area of the globe as you like. Again, this is also a real-time play of the actual session. And then you can unzoom and get back to the picture. So this is the first video clip. So give you some sort of impression on how this can be done by yourself once it is made available to you. You can also then select a new analysis time window. This time 6th of February this year. And you see now that the average thresholds, they have slightly higher values than for the other one. But you can also select the highest threshold during this day, and then you see it's saturated. This is the day of the large Turkish earthquake. And of course, then you can go and change the color scale. And then you see increasing to 5.5 totally stands out that this is an area where you can see the increase. And if you click on a point, you load the actual time trace data here, and then you see below there is a time trace showing the actual detection capability for this particular site. I have to go back again. I think it's swapping. Okay. And as you see on the lower trace here, there is a significant number of peaks, and each of these compares to the large signal from the two large earthquakes that occurred in Turkey on the 6th of February this year. Let me see if I continue. And then you can investigate these thresholds in more detail. You can iconify the time trace window. You can zoom in on the threshold trace. And then you can hover the mouse over the threshold to see that the detection thresholds vary significantly from around 3 before the event and then up to 5.5 or something, at least during the event. Also, you can zoom in on another area. For instance, North Korea is of interest, and see how this event influenced the detection threshold at another site of the globe. So in a way, this gives you a tool for any place on the Earth to get an assessment on how the detection performance is for the IMS primary seismic network. And again, you get the information by hovering the mouse over the trace or on the map also. And then you can reset the zoom to get the original 24 hours back on the screen, and you can unzoom and remove the traces as you like. Finally, of interest in the performance monitoring is to compare the performance today with the baseline. There is an icon on the lower right part where you can select a reference time window for which you compare the performance of today or at a time instant. And by clicking there, you can compare the detection performance on the 6th of February to the full month average of January, or any time interval of your liking, a year or a month or a few days. And you see that for the 6th of February, there is a slightly higher detection threshold than for the average month of January, which is to be expected because, as you've shown, there was a day with a lot of seismic activity that influenced the performance of the system. So I'm approaching the end of the demos here, just changing slightly the color scale. There are different color bar or color palettes available. And then you can, at the end, also show the instantaneous threshold at the beginning of the day, at the end of the day, and see how that varies. I'm just waiting for this to finish. I have no control on how. Again, this is a real-time video clip from my interactive session at NORSAR. And then at the end, you can get out of this mode, and then you get back to the sort of standard threshold map that you can play with, as I showed you. So, and then with relevance to performance monitoring, several of you are aware of the so-called validation acceptance test plan for the IDC, commissioning of the IDC. And one of the validations tests is about the performance monitoring that is available for any system. And we believe that this sort of methodology, which is general in terms of time and reference levels, can be a useful method for monitoring the performance of the IMS primary seismic network as a supplement to the other methods that are available. And again, this is a contribution from NORSAR. We are working together with colleagues at the IDC on this implementation. And we are hopeful that this will, at the end, become a success. So right now there is testing going on at the IDC. We are getting some feedback back to NORSAR. There are a few improvements that could be made. We also are discussing doing testing by the so-called alpha tester group. But once it is finished and approved by Working Group B, we hope that this will be made available to state signatories and authorized users through the secure web portal of the IDC. So thank you.
Thank you, Tormod. There is one question, and I think we should make time for that.
Hi, Tormod. Thank you very much for the excellent presentation. My question is because I'm working with station tuning, yeah, and that means that we change the thresholds of detection in IDC processing. Mm-hmm. So, and we change the fluxes of detections and events, and this defines our capability to detect events. But it's not relevant for threshold monitoring, because threshold monitoring uses different frequency bands in different detection beams. So essentially you somehow estimate in the different domain the possibility to detect signal, not what we have in our everyday processing. And what you say, detection threshold, is not related to the capability to detect events by IDC.
Well, it represents the 3-station detectability of the IMS primary network. Of course, if you go to 2 stations or you have different signal-to-noise ratio requirements, you will get a different number, or you have the 50% confidence. But I think this is a methodology that is agreed with the state signatories, that this is the sort of criteria that are used for defining events within the treaty requirements. But of course, if you do correlation detectors and other types of processing, you get a better result, but this is something that could be relevant for those who are interested in the performance of the network.
Would you want to comment on that very shortly?
From the evaluation point of view, I was happy. This is an evaluation tool precisely that should be doing things differently. So that's the very spirit of the whole story.
I think I'm sorry to interrupt this interesting discussion, but we need to leave the room at 5 o'clock, so we are there. And I'd like to thank all the speakers for their valuable contribution to the conference. Thank you.
Just a second. And sorry, we'll take the question to Bayaraa on the side because the screen is so small we didn't see it.
Yes.
But whoever asked the question will get an answer. Thank you.
Thank you.